Associated Universities Incorporated, the National Radio Astronomy Observatory, the Very Large Array, and the Very Long Baseline Array, welcome to the 25th Jansky Lecture. The Jansky Lectureship, which honors the founder of radio astronomy, Carl G. Jansky, is awarded annually by Associated Universities Incorporated in recognition of outstanding contributions to astronomy. This year's Jansky Lecturer is Professor Alan H. Barrett of the Massachusetts Institute of Technology. Professor Barrett is a graduate of Purdue University and earned his doctoral degree at Columbia University. He has been a Guggenheim and a Humboldt Fellow and was awarded the Count Rumford Medal by the American Academy of Arts and Sciences. He is best known for his pioneering work in molecular radio astronomy, beginning with the discovery of the hydroxyl radical. The title of his lecture this evening is Molecular Radio Astronomy, The Beginnings. Please welcome Professor Alan Barrett.
President and Mrs. Latman, NRAO staff and spouses, ladies and gentlemen. I'm very delighted to be here tonight and to be able to deliver the 25th Jansky Lecture. I'm going to be talking about the search for molecules astronomical environment, particularly interstellar space, which calls to mind a story of a molecular radio astronomer who was getting married, and his wife went to a shopping expedition to Tucson. And after picking out many things, she came around to picking out the nightgown, and picked out a very, very long and flowing gown with yards and yards and yards of material. And the sales lady that was waiting on her said, "Beg your pardon, but I have to ask this is a bit unusual for a wedding gown." And she said, "Oh, I know, but I'm marrying a molecular radio astronomer and he enjoys the search." So, here we go. Got the same kind of response in Charlottesville, I should have forgot it. When viewed from the perspective of 1990, it is difficult to believe the progress made in molecular radio astronomy in the last 25 years. In the early 1960s and before, the thinking was that only diatomic molecules stood any chance of detection. That is, molecules made up of two atoms. This conventional wisdom stemmed from the fact that the gas density in the interstellar medium was so low and the conditions so harsh that there would be a minuscule chance of making molecules of 3 or more atoms. And this seemed to be borne out by the fact that the only diatomic molecules which had been detected at the time was CH, that is a hydrogen and a carbon, and CN, a carbon and a nitrogen. They had been detected by optical techniques. There were a few pioneers, notably Shklovsky in the Soviet Union and Towns in the United States, who speculated on the chances of detecting molecules by radio techniques. Both highlighted the hydroxyl radical, OH, an oxygen and the hydrogen bound together, as a likely possibility. They disagreed, however, on the frequency where they thought the ground state microwave response of OH should be by about 25 megahertz or so, which doesn't sound like much, but when you're searching for a very, very small signal, having to search over a range of 25 megahertz is a significant job, especially with the equipment that existed back then. Towns also speculated on the possibility of some polyatomic molecules existing in the interstellar gas. And this calls to mind the story about the first IAU meeting I ever attended in the late 1950s in Berkeley. I doubt, judging from the age of the audience, that any of you were there at that time. But in one of the rump sessions one evening in somebody's dorm room at the University of California, I very well remember the subject of detecting molecules arose. And Tommy Gold, who has a way of asking very interesting questions, said, how do we know that there are not very complex molecules out there? What is the evidence that only diatomic molecules exist in the interstellar gas? And I so very well remember that. It stuck with me for these many, many years, because it turned out to be a very thought-provoking question indeed. More than a few radio astronomers expressed the view to me and to others that searching for interstellar molecules was not particularly worthy of telescope time, and the signals that detected would be so weak that they would be of very little value. It's been many years since I've heard that viewpoint, but it illustrates what some scientists thought of the future of molecular radio astronomy. As I was completing my PhD program at Columbia University in 1955, I went to my thesis advisor, Charlie Towns, and made known my interest in pursuing a career in radio astronomy. At that time, I was unaware of his strong interest in radio astronomy. He had. I was the first of his students to enter radio astronomy, soon to be followed by Pat Thaddeus and Arno Penzias. Towns steered me to NRAO, that is the Naval Research Laboratory. But before leaving Columbia, we discussed the possibility of detecting the OH radical. My office mate, George Bismanis, had measured the microwave spectrum of OH in the excited states as his PhD thesis. So in a sense, I was raised as a fledgling graduate student with George and following the details of OH even at that stage. Once you measure it, whether it's in excited states or the ground state, you know the molecular constants, and so you can calculate the frequency of the lowest microwave transition of OH, and it's the lowest one that you're going to be looking for in the cold environment of interstellar space. And that calculation turned out to be 1,666 megahertz, calculated frequency, which was amazingly accurate, but not known to be that accurate at the time. They assigned an uncertainty of plus or minus 10 megahertz. Undaunted, when I arrived at NRL, I teamed up with Ed Lilly, and we launched a program to detect OH. My job was to design a feed horn, a frequency doubler, and a mixer for 18 centimeter wavelength, which is the OH was. Shepherd it through the machine shop to test the final product. I don't remember what Ed Lilly did. Actually, the design was not very difficult because it was largely a matter of scaling it from 21 centimeters. When we had our equipment finished, and we mated it to what we call the back end, in other words, all the rest of the receiver that operates with almost any frequency you want it to, we mated it to the back end of the 21 centimeter scanning receiver. This was not the days of equipment like we have now, autocorrelators and things of that sort. We scanned a very small channel over a 20 megacycle chunk of the spectrum. 10 kilohertz channel, very slow. But we were ready to go when we mated all this new hardware to the scanning receiver. But we didn't have time yet on the NRL antenna. Well, we remembered that Ewan and Purcell detected the hydrogen line, the 21 centimeter line, by using a large horn antenna stuck out the window of their laboratory in Harvard. None of these fancy antennas or anything else, just a big horn stuck out the window. Well, at NRL, we were in a laboratory which looked south, and we had a big horn available that worked at 18 centimeters. So let's open the window and stick the horn outside and scan the galactic center when it comes by in the southern sky. And that indeed was the first serious search, in quotation marks maybe, for OH. We were still under the impression that the OH temperature, excitation temperature if you will, would be about 100 degrees as it was for the hydrogen line. It was only later that I did some theoretical calculations which showed that the OH would be anywhere near 100 degrees excitation temperature. It would be less than 10 degrees. So what that meant was the chance of finding it in emission, especially where the big horn stuck out the window, was not near as strong as we had anticipated, or as Towns and Schlafsky had anticipated either. Finally, we got our time on the antenna. We eagerly installed the horn and the receiver and began our search. We manned it 24 hours a day around the clock, and we looked for a characteristic absorption by looking at the strong radio source, Cassiopeia A. The reason we did that was because we knew what the hydrogen spectra looked like when we scanned the hydrogen line, Cassiopeia A. It has sharp absorption hits, and we thought they might be easy to recognize when we were looking for OH. We were hampered by interference. We didn't have the autocorrelator, which I've already mentioned. Therefore, it was a laborious experiment to do. The results spewed out on a strip chart that went on forever, and one had to average all those scans manually. It was awful. And all our efforts went for naught. We never saw OH. We did have one brief moment of excitement when we saw strong monochromatic signals, which depended very much on where we aimed the antenna, and boy, we thought, wow, this is it. But we were chasing meteorological weather in Washington, D.C. area, which transmitted 18 centimeters. Thus ended the first OH search. Now I'm going to switch to something you don't expect and take you on a little journey and describe the first attempt to detect the water vapor line in an astronomical setting. I didn't say interstellar space. In 1960, NASA decided there was a reasonable chance to launch a spacecraft to Venus using an Atlas-Centaur rocket combination. Planetary alignment dictated the date of July 1962. Now, 1960, 1962. This is not how planetary experiments are done nowadays. Not a 2-year lead time, no way. They go on forever. By way of background, maybe many of you know that the ground-based radio observations had shown the temperature of Venus to be about 800, 850 degrees Fahrenheit, which most people don't think of Fahrenheit. Well, most radio astronomers don't think of Fahrenheit, but anyway, that's what it was. And it was vital for NASA to know in planning the follow-on spacecraft experiments to Venus, was this hot temperature characteristic of the surface or a strong ionosphere? Either one had strong impact on how you would plan follow-on experiments to Venus. I had been doing some theoretical calculations on the radio spectrum of Venus, and so I was asked to participate in designing a microwave radiometric experiment to carry on the spacecraft to Venus and establish the origin of this high-temperature emission. Other objectives Got a long night. Other objectives were to establish the variation of temperature between the sun and the dark hemispheres of Venus, and upper limits on the water vapor in the atmosphere. So a radiometer experiment was devised with the radiometers operating at 1.9 centimeters and 1.35 centimeters, that one being on the water line, 8/10 and 4/10 of a centimeter. So we were going to bracket the water vapor line and scan the planet Venus as the spacecraft went by. And lo and behold, we know about the temperature of the surface of Venus, and we know about whether there was water vapor on Venus. Well, by mid-1961, halfway downstream, it became apparent that the Atlas Centaur rocket wouldn't be ready by July 1962. So a program review showed that a smaller spacecraft with a weight of about 500 pounds, whereas the original was to be 1,100 pounds, was able to be accommodated on this Atlas rocket. Well, the microwave experiment was cut in half. The 1.9 centimeter and 1.35 centimeter channels radiometers flew. The millimeter radiometers were thrown off. Therefore, we right away lost all our ability to place any limits on the water vapor in the atmosphere of Venus. What's more, the optical planet seeker was eliminated to save weight. So the scan program of all the instruments was to be actuated by the microwave radiometer. And that almost turned out to be a disaster for the entire mission. The radiometers were simple crystal video receivers because that's all the weight and power that one was allowed. And the microwave and kind of had two scan speeds. When we approached the planet and started up the apparatus, it was to scan rather fast, hoping to find Venus. And once we found Venus, then it was to scan at a much slower scan rate across the disk of the planet. The fast scan rate was 1 degree a second, and the slow scan rate was 1/10 of a degree a second. How would we know if we found the planet? By looking at the output of the microwave radiometer. Because when it went up, lo and behold, we had the planet. And so the scan logic circuitry would switch the scan speed from 1 degree a second to 1/10 of a degree a second and scan across the planet. It sounds perfectly simple. A scan reversal mechanism became armed when the radiometer output exceeded 2.25 volts. These are just numbers, but they do have some bearing. So that meant once we had acquired the planet and the signal from the radiometers went up to 2.25 volts and then dropped, that meant we were scanning off the planet, so the scan reversal mechanism would be actuated and we would scan back across the planet again. And we were supposed to get about 15 scans that way. Well, Murphy's Law takes over whenever it can, and it didn't quite work that way. Mariner 1 was launched in July of 1962 and immediately went off course, and the range safety officer had to destroy the spacecraft. Our colleagues were very kind and dubbed us microwave oceanographers. Unfortunately, we had the best instrument on Mariner 1. There was a backup, spacecraft and apparatus and everything else. Mariner 2 was launched on August 27, 1962, and began a 129-day trip to Venus. Every 190 hours in flight, the radiometers were calibrated, and it soon became apparent things were not going to work the way we had thought they would. The first slide, please. Hello. Hi, yes, thank you. It's slow. This just shows the history of the temperature aboard the spacecraft. launch to arrival at Venus. And it was designed to be about 35 degrees when we got to Venus, which was out here at, I didn't put down what day it was, but instead it was 58 degrees when it got, well, all right, this was when it arrived at Venus. It was 58 degrees. It was supposed to be 35. Well, okay, so what does that mean? Well, it means one thing, that it was very near to the 65 degrees, which experiments back at JPL had shown the whole radiometer would just quit. But the next slide shows you what really happened. It was so vital. Don't worry about this channel. That was the water vapor channel, and this is the gain of the channel. Well, you see, we started out on Earth with that nice strong gain. When we got to Venus, there was hardly any gain to it at all. But the important one is this 19 millimeter channel, and here's the baseline versus time, and here's the calibration signal versus time. Well, you see, when we started out, we had a nice strong gain. When you fire the calibration signal, we got a nice, good response. Lo and behold, when we got out here, we had zero gain at all. And when we got to Venus, it had reverse sign. It was negative. Now keep in mind, our scan logic circuitry is all based on this thing behaving this way. And it's not going to do that. It behaves this way. And notice, this is over the 1.5 volts. So we knew when we switched this thing on when we got to Venus, there was not going to be any fast gain, because the radiometer output was already over 1.5 volts. So the scan logic said, oh, good, we found Venus the minute we switched things on. So we'll start our nice slow scan. Well, we worried about this. 6.5 hours before closest approach, the spacecraft was commanded to enter the encounter mode. And after 129 days, this was the initial time that the antenna began to scan. And it did scan. We even wondered about that. But as I say, it scanned at the slow speed. What's more, there were no calibrations as it was approaching Venus, because the logic circuit said we're on Venus, let's not bother with calibrations while we're scanning the planet. We'll handle that downstream. So, you see what happened. Not only did we have the slow scan, but we were very near to 2.25 volts. In fact, we were at 2.1 volts. So we were within 15 millivolts of having the scan logic, which would approach the planet on a slow speed. As it reached the planet, as a result of the reversal of the gain, the signal would drop. The scan logic circuit would think we've lost the planet, let's reverse. So we almost had logic that completely avoided the planet entirely. We would have had, for 15 millivolts, we would have had egg all over us. But, I can do a little work here. We did indeed scan the planet 3 times. Okay, this is the slow scan speed. Oops, here we are, over here. This is the slow scan speed. Here we acquired the planet again on the second scan. And it went into fast scan because this signal stayed down so long. Remember, it's reversed now. On the planet, you get a lower signal. It stayed down long enough thinking we lost the planet, so it switched into the fast scan, which was very fortunate. So once it's in the fast scan off the planet, the signal rises again. The scan logic circuit says we've got the planet. Boy, let's go back to the slow scan. We went back to the slow scan, and we got this very lucky third scan across the planet. So this one was in the dark side, this one's across the terminator, and this one's in the light side. Talk about luck. If it had worked properly, we would have had 15 scans across the planet. Well, indeed, we got the scans across the planet. These are the 19 millimeter ones here, the ones with the strong signal, but with the reverse gain, as you see, scan 1, scan 2. This missing data was when it switched over to the fast scan rate, and scan 3 on the sunlit side of the planet. Here's the data for the other channel, which we just completely ignored because there's no sense in it. Well, there's nothing we could say about water vapor. Half an hour after closest approach, the spacecraft was commanded to return to the cruise mode. That stopped the scanning antenna. The noise tube fired, calibrating the radiometer. So we had a calibration after 7 hours of operation and within 1 hour of acquiring planetary data. And this was used in all our subsequent data reduction. And we got limb darkening on this, which means, don't worry about what it means, but it does mean that the high temperature originates, we can have the slide off, please, originates from the surface of the planet. But there was nothing at all we could say about the presence of water vapor. End of that story. Let's get back to OH and interstellar molecules. In the late 1950s, I was aware that Charlie Towns had a PhD student at Columbia measuring the ground state OH frequency. Why was that important? Once we know the frequency, we don't have to search plus or minus 10 megahertz as we did in the first search. We can concentrate on the known frequency. And at that time, I had moved on. I was at the University of Michigan as a postdoc, and I was constantly badgering Towns for when he was going to supply me with this magic frequency and also publish it. Well, in 1960, he published the results, until it was available from 1960 on. I went to MIT in 1961 when his Mariner experiments were underway, but I also began planning an OH experiment. Fortunately, something occurred which had major impact on our ability to do the OH search. And that was Jerry Wiesner had a graduate student who was working on building an automobile correlator. Sandy Weiner, you all know him, and know of him, you know him. But Jerry Wiesner went off to be science advisor to President Kennedy. And there was no radio astronomer or anything else on campus until I got there, and Sandy sought me out, and we became acquainted and teamed up. He completed his doctoral program, which involved 2 negative searches down in Green Bank with the correlator. One for the Zeeman effect and 21 centimeter line, the other one for the 327 line of Auditorium. But he came back to MIT and was hired at Lincoln Laboratory and brought with him his correlator. And so Sandy and I began thinking, why don't we do an OH search using the Lincoln Lab millstone antenna. It's not being used for radar experiments, ionospheric studies, and various other classified things that they do with it. Well, that was fine. We didn't want to have another negative search, but nevertheless, we were ready to give it a go. So in due time, an 18-centimeter receiver was mated with a correlator, with a Millstone field station computer, and their antenna, made available to us at nighttime. And in every way, antenna, receiver, correlator, ability to digitally average spectra, we were far better off than the original OH search 8 years ago. The first night we had everything hooked up and working. Not the first night we had everything hooked up and working. We saw OH and absorption against Cassiopeia immediately, 1964. This thing had been sitting around, the frequency had been available to the radio astronomy community for 3 years. And the first night we looked at it, with everything going, there it was. May I have the next slide, please? That shows the spectrum, if you will. Think of this here as being frequency, and this is received intensity of the microwave emission. That little light line that you see threading through there is the spectrum when we looked adjacent to Cassiopeia. And the wiggles are nothing more than noise. It's not saying there's any signal there whatsoever. The heavy line is what we see when we look at Cassiopeia, a strong radio source. You see there's very obviously a difference right here, right at the OH frequency. What's happening? There's an OH cloud, or there's a cloud with some OH in it, or a better way to say it, between us and Cassiopeia. When we get right on the right frequency, the OH absorbs the radio emission in Cassiopeia, and hence we receive less on Earth. So that signal right there is what we were so delighted about, how sweet it was when we got that the first night. And this is evidence that we were seeing absorption. Perhaps this is a good time to point out that I've been speaking of OH as if it was one line. There's really a multiplet of lines, 4 lines, because the energy levels of the OH radical get split as a result of the hydrogen, as a result of the spin of the hydrogen nucleus in this OH diatomic bond. And that's a complicated thing, which I'm not going to. We watched this thing over 2 weeks to be absolutely certain it was an extraterrestrial signal, because in 2 weeks' time, the Earth in its motion around the Sun alters its motion toward Cassiopeia enough that we can see a Doppler shift in the OH signal. And that's evidence, absolute table stomping evidence that it's extraterrestrial. You can skip over that next slide. I don't want to bother showing it. That has the energy levels of OH. Once our OH announcements or our OH results were made known, things began to happen rather quickly. Within 1 month of our announcement, 3 groups managed to detect OH. Here it had been sitting on the shelf for 3 years, waiting for somebody to get out there and show them how it's done. At the time, there was an international conference going on frequency allocations in Geneva, Switzerland. And there had been considerable discussion among radio astronomers, ad nauseum, some would say, as to what are the radio frequencies that radio astronomers wanted to see get international protection from interference. Obviously, the 21 centimeter hydrogen line was at the top of the list, and there was no argument about that. There was talk about the hydrogen line maybe ought to be safe, but nobody had detected the hydrogen line, so you really weren't able to build a strong case at all. But we had detected it while the conference was going on. So we hastily sent off a telegram to the radio astronomer in the U.S. delegation at Geneva, George Swenson, informing him of our detection. We were very naive to think that a last-minute result like this could possibly influence the U.S. position on frequency allocations, or world opinion on protecting the OH frequencies. Nevertheless, we got results from our telegram, even though they weren't the kind that we had hoped for. When George Swenson received the telegram, he immediately called up Vanderhulst in the Netherlands and asked, what's the possibility we were detecting OH in the Earth's atmosphere, not interstellar OH at all? Vanderhulst told him that the accuracy with which we quoted the frequencies of OH, even higher accuracy than was measured in the laboratory, precluded the fact that the OH we were detecting was indeed in the terrestrial atmosphere. I've always chuckled at this story because it says something about what George Swenson thought of our capabilities as radio astronomers. But nevertheless, he had his doubts. Well, after Swenson posted the result on the bulletin board, our telegram on the bulletin board. The Australian radio astronomer in attendance, John Whiteoak, I think it was, promptly telegraphed John Bolton's in Sydney, CSIRO, of the MIT results. This gave rise to an immediate reaction by Australian astronomers. In fact, I spent 6 months with them in Sydney some years later, and I learned about the reaction that set in when they got John Whiteoak's telegram from Geneva. Brian Robinson and John Bolton immediately started planning OH observations. When anybody else walked into Bolton's office, the telegram was quickly shoved into a drawer, and the subject was changed. They put together a receiver very quickly. Observing time on Parkes was preempted from the regular observer with great secrecy. The regular observer was a young American postdoc by the name of Ken Kellerman. And he was kicked off the telescope. And right away they detected OH and absorption against the galactic center, and the telephone rang in my office at MIT. Bolton had telegraphed me to say that they had confirmed our detection of OH. I was elated because this was the initial result. Subsequently, within the month, Dieter and Ewan, Dan Dieter and Doc Ewan, the same Ewan of 21 centimeter fame, used an Air Force antenna in Hamilton, Massachusetts, and Weaver and Williams at Hat Creek put together a receiver and right away detected OH, both of them in absorption against Cassiopeia. At the same time, Arno Penzias was using the horn antenna that you've seen pictures of at Bell Telephone Laboratories, and he was trying to detect OH in emission in the galactic center, anticenter, in the anticenter. The idea being that the background noise is going to be a minimum there, and that meant then that he might have a hope of OH emission being seen in that region. I think it's very nice for both of us that he didn't succeed. One, if he had succeeded, he might have beaten the MIT group out of finding it. But he might also have become so preoccupied with his OH studies that he wouldn't have bothered to chase down this ridiculous little 3-degree signal that he had in his background with his receiver, and thus missed out on detecting cosmic radiation, background radiation, and missed out on his Nobel Prize. So I think he's probably just as glad as I am that he didn't see OH. The astronomical grapevine was working pretty well, very efficiently. But there was still great interest when I presented the OH results at a meeting of the American Astronomical Society in Pittsburgh. Arno Penzias spoke just ahead of me about his negative results of trying to detect OH in emission in the anticenter. And then I spoke of our results, which was absorption in Cassiopeia. The chairman of the session was not a radio astronomer, and when I got through talking about we had detected OH, Arno got through talking about they hadn't. He asked Arno if he had any comment on our positive result in view of the negative result. Penzias indicated that there was no conflict in the two results whatsoever. So he sulked back to Bell Telephone Laboratories and started studying a ridiculous little leftover signal in his apparatus and won a Nobel Prize. I went back to MIT all happy about our big accomplishment and proceeded to shove forward the frontiers of molecular radio astronomy. Incidentally, it was that same year that I got tenure at MIT, and it was only after I got tenure at MIT that I let it be known they had turned me down for admissions of freshmen shortly after World War II. What goes around comes around. The Australian detection of OH in the galactic center was not without its difficulties and surprises. They went at this, as I have indicated, very quickly and rapidly. They retuned their hydrogen line receiver from 1420 to 1660 over 200 megacycles. And that raised the possibility that they would have severe baseline problems. And indeed they did. The story goes, which I think I heard about first from Mark Price, John Bolton was about to, would retune the 21 centimeter dipole feed using a hacksaw. Well, if you're going shorter wavelength, you can get away with that. And he was about to do the same thing on the parametric amplifier with the same delicate instrument. But that wouldn't have worked. Brian Robinson, the receiver expert, took over and retuned the receiver. Nevertheless, they were expecting difficulties when they searched in the galactic center. And they indeed had them. The next slide shows a little more than I want to talk about right now. But this little dotted line in here is the strong absorption response of hydrogen in the galactic center. So the Australians and anybody else who naturally figured that you'd get the same strong response at the same value of the frequency in OH. So they were searching from here to here in OH initially. And sure enough, there's this little dip right in here, right at the right spot matching the hydrogen. But it's on this horrible baseline, what they thought was a baseline. Well, when you retune these receivers 200 megacycles, you almost expect baseline problems of the sort. So even though they had this little bump here, and they had it at 1665 and 1667, which are the OH lines that I spoke about, the actually multiple lines, not one. So they removed their apparatus from the antenna, retuned it, did everything they could to make the baseline go away, and nothing happened. When they put it back on the antenna, they got the same sort of thing. So finally they scanned from here over to here, and they realized that this sloping baseline was really the edge, or half, of a very strong pumping OH absorption signal. It's all real with OH. Much stronger than anybody ever anticipated. And that was a real surprise. That wasn't really the end of it, because when Harvard looked at the OH in the galactic center, they found another whole section of OH absorption over here. So the OH spectrum, if you will, looks like that. The OH signature is the solid line in absorption against the center of the galaxy. And the dotted line is what the hydrogen spectrum looks like. And everybody figured that the OH spectrum mimicked the hydrogen spectrum. No way. Not at all. If I may have that slide off, please. Thank you. Well, all these studies were in absorption, and there's strong physical reasons why one would want to find OH in emission. The reason being is if you see OH just in absorption, you don't know the temperature of the gas, nor how much OH is between you and the observer, you and the radio source. And it's the temperature of the gas and how much that are the astrophysically important things that one wants to get at. Not just the fact that OH is there. So immediately, one began looking for OH in emission, because if you see OH in emission and absorption, then you've got two measurements, not exactly in the same path, but nevertheless two measurements, and then you can unscramble this business of the temperature of the gas and the amount of the gas, the column density. So right away, people began looking for OH emission. And nobody was ready for what happened. Groups at both Harvard and Berkeley detected OH emission almost simultaneously. But it didn't behave like OH was supposed to behave. In the first place, the 1665 megahertz line is supposed to be 5/9 as intense as the 1667. Just to work that out theoretically from the statistical weights. Instead, what turned up was that the emission was largely at 1665, very, very strong, and hardly detectable at 1667, which is supposed to be 9/5 times stronger. The Berkeley people named what they had discovered Mysterium, because they didn't think they had OH at all. They thought they had some new molecule or something or other which was radiating at 1665. At Haystack, we jumped onto this and worked a little harder. We had a little bit bigger antenna. And we detected OH emission at all the frequencies that OH is supposed to radiate at. But indeed, it was vastly stronger at 1665 than it was supposed to be. Very much. So Mysterium was really OH, even though Mysterium was a very apt name for it because it was mysterious. And that began right then and there, the first talk that maybe we were detecting the maser emission. Now, for those of you who are not aware of what maser emission means, it somehow means that nature has transpired to create within this cloud to invert the populations of OH radicals, molecules, if you will, in such a way that it becomes a giant amplifier of its own signals. How could nature do this in the interstellar gas? But if the whole cloud was an amplifier, maybe only at 1665 for some reason, then you'd get whopping big signals at 1665 megahertz, and you'd have a hard time seeing it at the other frequencies. Well, that's indeed the situation. We put a lock on this for sure when we were observing at Haystack, and noticed that the emission seemed to vary as we tracked the source across the sky. Well, that's a peculiarity of the Haystack antenna versus any other radio telescopes, but it was the clue that OH was polarized. I won't go into what that really means. I don't think it's necessary, but it did mean for sure that OH was somehow masering out there in the interstellar gas only itself. There were other indications. The emission intensity was 1200 degrees at that time for the antennas that were being used. And that was much higher than anybody anticipated and polarized. So everybody was convinced we had an interstellar maser. It's interesting to speculate the chain of events that might have occurred if the maser had not been invented in the laboratory first, had been found first in the interstellar gas. That one is mind-boggling. The fact that OH was the result of one or more interstellar masers dictated very clearly the next step in OH observations, because if it's a maser, it had to be coming from a source of very, very small angular size, much smaller than one could ever hope to detect with a single antenna. So one began doing OH interferometry, that is, studying them as separate antennas and correlating the signals from the two antennas and establishing the size of the emitting source. And one quickly ran out of having antennas with which one could do that with the conventional way of doing interferometry. But this VLBI technique was just getting underway as the OH here one had strong monochromatic signals and it was ideal for a number of VLBI experiments. So a long series of VLBI experiments were done. And the angular size of the OH emitting regions became very, very small, of the order of 1/100th the size of the solar system. And that meant that the temperature at which the OH was emitting was 10 to the 9th degrees. That's a 1,000 billion, if you will, degrees. That has no physical meaning whatsoever, but it certainly is another indication that it's a laser. Well, I've been speaking entirely about OH because it was the first molecule detected by radio techniques. It was the first evidence of interstellar masers and my own personal involvement. But other things that were going on that were not equally important, they were more important to molecular radio astronomy than the OH. And Towns, as I mentioned at the beginning, had some polyatomic molecules on his list. And he had left MIT at that point and gone out to Berkeley. And he interested Jack Welch in looking for ammonia at Berkeley. And also, we were beginning to build a ammonia radiometer at Haystack. But we weren't working on it as fast as he was because we were also doing a feed for 18-centimeter polarization studies at Haystack for OH purposes. And the engineering group at Haystack is very limited in terms of doing things in spectroscopy, not nearly as limited as you know in VLB work. Well, one thing led to another, and the ammonia was detected at Berkeley very quickly, and they also detected water vapor, which has frequencies very, very nearby. Water vapor turned out to be another interstellar maser, like OH was. Very, very intense signals from water vapor. And in fact, they're so intense that had one done it many, many years ago, maybe even before the hydrogen line was detected, water vapor might have been detected in the interstellar gas. But that's all hindsight, of course. But anyway, the logjam was broken. The myth of only diatomic molecules in the interstellar medium was shattered. There were more complex things out there. And once the floodgates were open, things began to happen very quickly. Snyder and his associates shortly detected formaldehyde, and many, many other molecules followed in the next few years. The list now numbers over 100, and some of them are not even known on Earth, but they are detected in the interstellar gas. Rather a striking thing in itself. The most important molecule discovered I have yet to mention, and it's a diatomic one, oddly enough, CO, carbon monoxide. That was detected by Penzias, Wilson, their associates at Bell Telephone Laboratories, and it opened up the field of millimeter wavelength observations of molecules, which is where almost all the action is, not entirely. But it's difficult to overemphasize the importance of CO in the study of the interstellar medium, because it is ubiquitous and an excellent tracer of molecular hydrogen. It was through the study of CO that one became aware of the existence of what has become called the giant molecular clouds, the most massive structures in our galaxy, with the possible exception of a black hole, which is buried there. They have densities of the order of 1 million hydrogen molecules. The molecular clouds have densities of the order of 1 million hydrogen molecules per cubic centimeter. And the masses of these clouds are 1 million to 1 billion times the mass of our sun, which is the standard unit of mass in astrophysics. There is not an area of molecular astronomy that has not been influenced by carbon One example of a giant molecular cloud in its role of star formation is shown in the next slide, which is the this is the Orion Nebula, which is arguably perhaps the most well-studied region in our galaxy, certainly by the molecular radio astronomer it is, because it is nearby, it is a region of star formation, and it is a great chemical factory. Almost every molecule that's been found in interstellar space either has been found in Orion or subsequently shown to exist in Orion. It is what is known as an H2 region, which means it has hot young stars and they're spewing out ultraviolet light because they're hot, ionizing the hydrogen that happens to be nearby and making a mix, if you will, of electrons and protons, which are the end product of ionizing hydrogen. The hot stars ionize the gas nearby, and stellar winds, which are streaming atoms coming out of these stars, of density inhomogeneities, i.e. clumps, and thereby give rise to maser emission, OH, water, a few other molecules, and eventually become protostars, the sites of where new stars are being formed. Another example of a giant molecular cloud and its role in star formation is shown in the next slide. It is the Omega Nebula. No, that's the that one is the Rosette Nebula, which is another example of an H2 region. But the next slide, here I can do this. The next slide is the Omega Nebula, and depicts the interaction between the H2 region and the molecular cloud, which is all this region over in here, where there are there's an IR object buried there, which is another hint, IR infrared. There's CO contours, which means that there's a lot of hydrogen there and CO. And the interaction between the H2 region and the cloud is this dotted line right along here, which is the shock wave from the ultraviolet, and is the region where new stars are being formed. New stars are being formed on a time scale of the order of 1 billion years or so. Note the CO contours on the edge of the H2 region, that is this whole thing here. Because that is what is indicative of high density molecular hydrogen. The next slide shows this whole process in a schematic kind of a picture. The young O and B stars, so-called, the hot stars are occurring here. The ultraviolet comes out from the stars, it ionizes this whole region, starts it expanding. It interacts with the molecular cloud here, which is just this huge region, relatively cold gas. And the shock wave makes density inhomogeneities, and the maser emission, and the beginning of more new stars. Why I keep talking about these giant molecular clouds, I should point out, however, that the molecules that the radio astronomers study are an extremely small constituent of these clouds. Well, if it's a small constituent, why bother studying that? Why not study the main stuff? Well, that turns out to be molecular hydrogen. The molecular hydrogen, two hydrogen atoms bound together, homonuclear molecule, if you will. And therefore, for reasons I won't go into, it does not interact with microwaves as it rotates. So molecular hydrogen, which makes up the vast majority of the mass matter in the universe, is undetectable. And in a way, that's a good thing. Why do I say that? Because we live at the bottom of a sea of homonuclear molecules, nitrogen and oxygen. And if homonuclear molecules had microwave lines, we wouldn't be doing radio astronomy in this surface of the Earth. So you win some, you lose some. And even though hydrogen molecules are a billion times more abundant than some of these other things like ammonia and water, cyanoacetylene, these crazy things that exist out there, you can't study hydrogen. So I notice in concluding that the whole field of astrochemistry has arisen as a result of the complexity of the interstellar gas as revealed by radio astronomy. Polyatomic molecules not only shattered the myth that only diatomic molecules could survive, but spawned the field of astrochemistry. How do you create and how are these molecules destroyed in the harsh interstellar environment? And there would be no such field as astrochemistry if there were only diatomic molecules in the interstellar gas, like OH. It's the fact that these other complex things are there that has given rise to astrochemistry. So from the slow, stumbling beginning of molecular radio astronomy, has become a dynamic and important specialty of astronomy and astrophysics. The complexity of the interstellar gas is now very, very well known, even if not understood. Esoteric molecules have been discovered. Nature's measures have been found in many molecules, not just OH and water, which I've mentioned, but also silicon monoxide, methyl alcohol, somehow managed to amplify their own signals. Molecules are being studied in a routine nature in extra galactic objects, other galaxies besides our Milky Way. A huge new impetus has been given to the study of star formation. All our thoughts have had to be rethought about star formation. Extragalactic masers have been found, so-called mega masers. Huge, tremendous thing for a whole galaxy seems to be amplifying. Doesn't make any sense whatsoever. That's the way it is. So one can confidently predict that as millimeter and submillimeter antennas and equipment improve, some radio astronomers are going to have a whale of a lot of fun studying interstellar molecules. Thank you.